Hey everyone, welcome back to The Explainer. Today we're taking some pretty dense chemistry notes and flipping them into a full-on, step-by-step detective investigation. Seriously, we're going to dive right into the hidden world of everyday chemistry to unmask the true identities of some seriously elusive chemical culprits. It's going to be fun. So let's kick things off with the ultimate laboratory dilemma. You already know from everyday life that certain things are sour, like lemons, right? While others have this distinct bitter edge. But in a chemistry lab, we can't exactly go around tasting everything to figure out if it's a sour acid or a bitter base. That is literally incredibly dangerous. So, without using our sense of taste, how exactly do we interrogate these unseen chemicals and figure out what they really are? To solve this mystery, we've got a really clear investigative roadmap. First up, the acid-base basics, then visual chemical detectives, followed by the scent of chemistry. Next, reactions with metals, and finally, we wrap it all up at the neutralization point. All right, let's jump straight into Phase 1. Section 1, the acid-base basics, meeting our prime suspects. Let's take a look at the fundamental nature of our two main culprits. First up, acids. Now, if we could taste them safely, they'd be sour. In the wild, they're highly corrosive, they pack a real sting. And chemically speaking, their absolute signature move is producing the H+ ion. Then, in totally stark contrast, we have bases. They're pretty much the exact opposite. They are bitter, they feel super slippery or soapy to the touch, and they produce the OH- ion. Basically, these are the chemical fingerprints we're hunting for. Just to ground these concepts, let's pull a few specific suspects straight from our case files. For the acids, we're dealing with heavy hitters, stuff like hydrochloric acid, or HCl, and sulfuric acid, H2SO4. Over on the base side, our usual suspects include sodium hydroxide, which is NaOH, and magnesium hydroxide, MgOH2. These are the exact chemicals we'll be tracking and testing throughout this investigation. And that brings us to our next phase, Section 2, Visual Chemical Detectives, Identifying Suspects by Sight. So how do we unmask these guys without tasting or touching them? We use specialized tools. The key definition to know here is an indicator. It's simply a substance that changes its color to show an acid or a base. Think of them as our chemical informants. They literally shift their visual appearance to betray a chemical's true identity, letting us see what is otherwise totally invisible to the naked eye. Let's actually walk through this matrix of visual tools. Take litmus, for example. It turns red in an acid, but blue in a base. Or what about a totally natural tool like turmeric? It stays yellow in an acid, but turns a deep, dark red when exposed to a base. Actually, think about a time you might have dropped, say, a yellowish curry stain on a white shirt, and then scrubbed it with slippery, basic soap. It turns reddish-brown, right? That's chemistry in action. And check out the synthetic indicator, phenolphthalein. Try saying that 3 times fast. It stays completely colorless in an acid, but the exact moment it hits a base, boom, it flashes this striking pink. Oh, and here is a fantastic little detail. You know that litmus paper we rely on so heavily? Well, it's actually not born in a lab. Litmus is a natural purple dye extracted from lichen, which is this resilient little plant belonging to the division Thallophyta. So our absolute most famous chemical detective is actually derived straight from nature. How cool is that? Let's see how this builds into our next phase, Section 3, the scent of chemistry, olfactory indicators. Because visual clues aren't our only tools, right? Sometimes just the very smell of a room can help solve our mystery. By definition, an olfactor is a substance that changes its smell in an acid or a base. So we're moving way beyond just the visual and tapping into the sensory. We're literally letting our noses do the detective work. The really crucial point here is how these olfactory indicators actually react. If you take the strong, super distinct scent of an onion or the sweet aroma of vanilla and expose them to an acid, nothing happens. The smell just stubbornly persists. But introduce those exact same scents to a slippery base and the smell completely vanishes. It's honestly like chemical magic. If your vanilla suddenly loses its scent, you know for sure you've caught a base red-handed. Now that we've identified our suspects by sight and smell, it's time to turn up the heat. Section 4. Reactions with metals, the interrogation room. Let's take a look at this laboratory setup, because this is where we put our chemicals under some real pressure. We take zinc granules, which are, solid metal, and drop them into a test tube filled with dilute sulfuric acid. We're essentially forcing a dramatic reaction to see exactly what this acid is capable of when it's provoked. So here's the precise step-by-step procedure for this little interrogation. Step 1, you add those zinc granules to the dilute acid. The second you do this, a gas immediately starts bubbling up. Step 2, we capture that evolved gas by passing it through a delivery tube and straight into a soap solution, which creates these gas-filled bubbles. And finally, step 3, we take a burning candle and bring it right up near those rising bubbles. And what happens next? Well, we get definitive auditory proof. The bubbles ignite. The notes capture this perfectly. Burning of hydrogen gas with a pop sound. This pop test is absolutely legendary in chemistry. It proves without a doubt that the acid aggressively reacted with the metal, displacing the hydrogen atoms to form highly combustible hydrogen gas. The acid has totally revealed its true strength. And finally, we reach the resolution of our investigation. Section 5, the neutralization point. Case closed. So what actually happens when our two elemental opposites, the corrosive acid and the slippery base, finally collide in the same room? Well, they battle, but then they just completely nullify each other. This is the ultimate resolution, the neutralization reaction. Simply put, a base plus an acid yields a salt plus water. So for example, if we take our base suspect, sodium hydroxide, and mix it with our acid suspect, hydrochloric acid, they literally destroy each other's distinct properties. All they leave behind is plain water and sodium chloride. The chemical hostility is completely erased. Looking back at the aftermath, the results of this massive clash is the salt family. A salt, like sodium chloride, is really just a stable combination of a positive cation from the base and a negative anion from the acid. They just lock together, perfectly neutralizing the threat. Now, you might be wondering, why does this matter outside of a laboratory setting? Let's connect this amazing science straight back to real life. Think about it. If someone in your family is suffering from acidity after overeating, what's the remedy? Well, think about what we just learned. The problem is excess acid in the stomach. That's the corrosive sting we talked about back in phase 1. So naturally, the scientific solution, our chemical detective remedy, absolutely must be a base. By introducing a mild base like baking soda to that acidic stomach environment, you're triggering a neutralization reaction right inside your own body. The base nullifies the acid, produces harmless salt and water, and boof, the stomach pain vanishes. So as we officially close this case file, I want to leave you with one final thought. We've just seen that turmeric from the spice rack and lichen from the forest floor are seriously powerful chemical tools. We know that baking soda is a neutralizing base. If these natural indicators and chemical balancers are just sitting all around us, what other hidden chemical reactions are waiting to be uncovered in your kitchen right this very second? The world is literally your laboratory. Keep investigating, keep questioning, and I'll see you in the next explainer.